Hi everyone. Today I'm going to be going over question 10.56 from the bingo problems. This problem says a uniform 8.4 kilogram spherical shell 50 centimeters in diameter has 4 small 2 kilogram masses attached to its outer surface and equally spaced around it. This combination is spinning about an axis running through the center of the sphere and 2 of the small masses. What friction torque is needed to reduce its angular speed from 75 RPM to 50 RPM in 30 seconds? So, first of all, two equations we're going to need. We know that torque is equal to the moment of inertia times the angular acceleration, so we're going to need that. And then we also know that the moment of inertia of this system is going to be 2/3 mr squared, and this is going to be the mass and radius of the sphere, plus 2 times the mass times radius of those little masses attached. And so what we're going to do is, first of all, let's change these angular velocities from RPM to radians per second. So to do that, let's start with the first one. So initial equals 75, and that's going to be, we'll just say rev. I know it's technically rotation, but they mean the same thing. Per minute. And we know that 1 revolution is equal to 2 pi radians, and 1 minute is equal to 60 seconds. So now we can cancel out our revolutions, cancel out our minutes, and we end up with radians per second, which is what we're looking for. So we plug that into the calculator, and we get about 7.85 radians per second for the first one. And then we'll do the same thing for the second. So honestly, we can just replace this number here with the final value and do the same thing. So that one ends up being about 5.24 radians per second. All right, now that we've done that, all our units are where they need to be. So now what we can do is we can find that moment of inertia. So we know, so let's plug the things in that we know. So we know that the moment of inertia equals 2/3 times the mass of the sphere, which is 8.4 kilograms, times the radius squared, which is going to be 0.25 squared, plus 2 times the mass of the little masses around, which is going to be 2.0 kilograms, times the radius, 0.25 squared. And when we plug all this in, we end up getting that the moment of inertia is equal to 0.6 kilograms times meters squared. Now what we can do, so we know the moment of inertia, so we know one part of our torque, right? Because that's what we're aiming for. So the next thing we need is our angular acceleration. So I'm actually going to write the moment of inertia up here. and give myself some more room. So now what we need to do is find the angular acceleration, like I said. So we do that by finding the difference in the angular velocities over the time. Since we know that we can start the time at 0, technically it would be t final minus t initial. Since the initial is 0, we can just say time. So anyway, so that's what our angular acceleration equals. Since we know these values, we can plug them in. So it's going to be 5.24 minus 7.85 over our time, which is 30 seconds. And these are radians per second. And throw that in the calculator, and we end up with negative 0.087 radians per second. I think I just said radians per second. I meant radians per second squared, since it is an acceleration. So now we have all we need to find the torque. And so we know from up here that the torque is equal to I, which is the moment of inertia, times the angular acceleration. Since we've found both of those, we know that it's going to be 0.6 times our negative 0.87 and throw that in the calculator, and we end up getting that the torque must be equal to negative 0.052 Newton meters. I'll write that a little bigger up here. So there's our answer. So that means that in order to slow this sphere down from 7.85 radians per second to 5.24 radians per second in a time frame of 30 seconds, we would need to apply a torque. So obviously it's negative because it's in the opposite direction of the way the sphere is rotating, of negative 0.052 Newton meters. So that makes sense. I mean, it's kind of a small torque, but you have 30 seconds to slow it down, so that makes sense that you don't need a ton of torque to do that. But anyway, that is the end of the problem. So hope you learned something, and see you in the next video. Thanks.